Alright, time for another draftphysics.com, debatephysics.com, but yes, the debate is hard to find. It's hard to find people willing to argue their positions. You know, they just say stuff and they want you to believe, and you don't have to make an argument. A very good one. One that has, interrogation involved. And we all should be interrogated. And this is good for the truth and good for intelligence and expanding our understanding and all of that and refining it and making it, giving us integrity as opiners on any subjects. That's how you gain integrity, is to actually win. Actually win the argument with evidence and substance, not just your own declaration. So anyway, this Harry Rinker guy, the John Chappelle something or other bullshit society, whatever. It's good that the little dissidents have some place to go to do their ragging, and that's mostly all they do. So anyway, they spent 4 hours so far, I guess, on this subject of the Faraday paradox, and it's an interesting subject, but they're doing no good background. So there's no way to exactly understand anything being argued because they don't illustrate it very well or define very well what the substance is. And the circumstances that exist and what the experiments, what you can glean out of them and what you can't, because of the noise being created by all the dissonance, frankly. The 400,000 different people who think they're going to make free energy and all that kind of crap. And so they do a bunch of kind of bent and crooked experiments, like Brozo, because they have an agenda. All right, anyway. So I think I'll add what I think is missing from their conversation, a key ingredient, which is a little clarity. And I'll add what I think fertile ground might be in terms of understanding the paradox and how it affects other aspects of physics, that this paradox exists in by more than one definition. It's not just the Faraday paradox. There's a lot of paradoxes. Physics has got a lot of paradoxes in it. So anyway, so the idea is that you take a disk. Can you see that? Not really. Well, let's see if I can make it thicker. Can you see that? Yes, that's almost visible. Almost. Close enough. Alright, and you spin it. Alright. And the idea is to spin it in a magnetic field. So you have a north-facing magnet here. So in the first case, you just spin a copper disc in a magnetic field. And you get a voltage. So we'll just, for a voltage, we'll just put an up arrow, volts. Alright. And then if you spin the magnet instead, alright, so you just spin the magnet and, rotation arrow. And the disc is stationary, so we'll just draw this line. Then you get no voltage, so 0. Alright, put a line through it. There. That's basically the experiment. Then the idea is you spin both of them and you're back to having a positive voltage. So the theory is, so I just put the north and you have the disk and you spin both of them. Both of them are spinning and you get a positive voltage again. So I'll put a plus here. Alright. So what you can notice is that the only time there's a voltage is when the disk is moving, and it appears to not matter if the magnet's moving. And that this is about lines of force, what are called field lines and magnets. So Faraday's theory, to add some clarity, let me try the other marker just for the hell of it, because that is a little bit Faraday, I don't know if he was the first one to do the simple iron filing thing, but there's this idea that the magnet creates these field lines, And the problem with that is, I've explained it over and over again, is these are arbitrary lines. They're really not the substance. They're the effect of when you put, and what the little iron filings are essentially little magnets. Okay, that's all they are. They're just little magnets, the iron filings. And they are sympathetic in terms of how they're going to align. And so they're all aligning south-north. Alright. And obviously when they group together, they become a magnet themselves that repels other south-north magnets. So all of the south-north magnets being created in these lines are repelling each other. That's why there's empty spaces here. The empty spaces have nothing to do really with what the magnet's doing. They have to do with what the filings are doing. So if you use really fine filings, you'll get little fine lines. Use big filings, you'll get big thick lines. The lines are not physics. Alright, the real physics of what's happening here is Maxwell's drawings of charge. Okay, and his drawings of charge will demonstrate that what's the real field lines are radiating from the charges. These are the real lines of force. Okay, if we're going to use, to use vernacular, these are the lines of force. Alright, these are the lines you would cut. And these are the lines that would decide how, if you're here, and you're going to say how powerful is this charge, then you'd measure it by how many of these lines intersect you, and that'll tell you, it's an arbitrary lines, right? You can have 1,000,000 lines, you can have 10 lines. You're just measuring how many did you bisect, and that'll tell you how strong the force is. So it's just a way of measuring the force. You could just measure it by measuring how much it pulls on a magnet. You could measure it lots of ways. This is a mathematical way of measuring it. So this is really a kind of semantics. The difference between, Faraday saying these are the lines that matter. Maxwell is saying these are the lines that matter. So Maxwell's idea is that the magnet is still producing these kinds of lines. Alright, and you're really just saying how close are you to the damn magnet. How close you're to the magnet will decide how much field you're being affected by. So you measure the field by, it's a real thing. And again, it's just this confusion over a field line and a line of force. And they're different things. They should be called and understood to be different things. And, the physics is messed up. So there's no real conflict between Maxwell and a Faraday perspective, except in the sense that, yes, Faraday is kind of crude in thinking these lines mean something when they're arbitrary. And the real lines of force are just how close are you, because it's the inverse square law, frankly. Alright. Because it's a magnet, it's a little different. It's the cubed law, but it really doesn't follow that law. Because you're basically saying you're getting pulled by one side, you're getting pushed by the other side, to use vernacular, okay, but from a dipole. So obviously, depending on where you are, you'll have an equal amount of force placed on you from the two poles of the magnet. Alright, so the underlying idea is the simple one that this is really what Maxwell turned into an equation. It's just the idea that if you're a wire, well, let's do it as a coil because it works better. You're just saying that how close the magnetic field is. So does it stay the same or does it change? And so you're really just talking about every time you move it closer, obviously you're moving into more field, and you're going to change the structure of the atoms. And if you move away, you're going to change the structure of atoms, and it's the speed that really makes a difference. How fast you do that will decide how much electricity you can induce in the wire, okay, as a consequence of doing this to the atoms. Causing the atoms to turn to the magnetic field. And the atoms turning has the consequence, a side effect of creating electricity. Alright, So in all these experiments, it's a tiny amount of voltage you're getting across. You're measuring the voltage from the center of the disk to the outside of the disk, and it's a tiny amount of voltage, tiny amount of current. All right, wattage. So you're not generating a whole bunch of electricity. You're obviously putting a lot more energy in to spin the disk than the disk is producing in electricity. You couldn't run the motor anywhere close to running the motor. You need 1,000 of the disk's voltages to make one of them run, to spin one disk. Might be 10,000. It's a very low current. All right, see if there's any other point to make. So it's cutting lines isn't really what this whole thing is about. Okay, that's just a way of making it simple. So it's a simple mathematical way of drawing the inverse square law. So it's just really doing this geometry thing of just demonstrating that you're spreading in 2 dimensions. You're getting wider this way and you're getting wider this way, and that's why it's squared. So as you go further out, okay, you're expanding the square in 2 dimensions. So you're 4 times, twice the distance, 4 times, you could say, the surface area, or the real area of the square you're creating. So that's why there's less effect with distance, dramatically less, right? Half the distance, 4 times the difference in the size of my hand. So you're diluting the force with distance by the squared rule. And so these lines just are a way of drawing or understanding that principle. All right. Right, so Maxwell's about distance and movement, and Faraday's about a cheat of saying, well, how many of these lines did I cut across? And that's really not the subject. All right, so so back to the real experiment. The fact that you have this commonness that the only time you have electricity is when the disk is spinning. All right, so that's it. The disk has to be spinning or you're not going to get anything. And so, the idea would be is that if the magnet's spinning, those lines are spinning, and it should be creating electricity. So it's really not about lines. And obviously the pressure of the magnetic field would be rather consistent, so it wouldn't change how close you are to the magnet by spinning the magnet. Doesn't make any of the pieces say, oh, the magnet came closer to me, the magnet moved in, or the magnet moved out. Spinning isn't moving closer and further away. So by Maxwell's diagram, there's no paradox, because that's exactly what should happen. The tricky one is this one to explain. So when you're spinning both the magnet and the disk, now you have a voltage, and that's the one where you say, well, why would that be? So, one commenter in the John Chappell Club brought up the fact that you are spinning the disk, and you're in fact causing motion inside the structure. All right, we'll give up on this one. Let's see if this one works. Yes, I don't know if I should redraw this. So when you're spinning the disk, all right, you're causing, obviously you have a higher velocity for the atoms on the inside, right? So, make a circle, right? The ones on the inside are moving much slower, right? They have a small velocity arrow. The ones on the outside have a high velocity arrow. So right there you could say that conflict is probably causing something. And you can sort of understand that what happens is the faster something goes, the more it wants to just fly off in a straight line. And something has to pull it back. Something has to cause it to stay. Now, there's no gravitational force doing it. There's no, like, the gravity pushing us back up. There's no physical mechanism keeping the stuff connected to the copper disk. The only thing that can be doing that is the elasticity of the atoms themselves. So essentially, when you're spinning the disk, you're stretching the atoms. You're pulling them apart with a force, okay, and it's an uneven force. there's more pulling on the atoms out here than there are here, and therefore you could say there would probably be a lot of movement of the atoms in fixing that differential. The atoms want to all be at the same state. They want to be at the same charge, so to speak. And so they're going to try to force that imbalance between the pressure on the electrons out here and the pressure on the electrons out here in here. And in doing that, they're going to be doing a lot of oscillating. So now they're moving side to side, okay, in that magnetic field, okay, even when the disk is spinning. Because even when the magnet's spinning. Alright, so when the magnet's moving, God, these are just terrible. They erase is better than they draw. Disappointing. Let's see if I really smash on it. Yeah, if I really smash on it, I can get something. Alright, so it's sort of like something being on a spring and it's going to oscillate. So you're causing motion of the atoms, okay, across the magnetic field. And you know, that's at least a way of understanding why there's electricity being created, because the atoms are constantly changing their shape. So if we argue that electricity is created because an atom goes from a certain amount of pressure, okay, and then it polarizes when you introduce an electron with a higher pressure, the atom effectively just changes shape. You know, it polarizes. It becomes a dipole. Dipole, or even a tripole. Okay, it becomes more negative going this way and more positive at both of these ends, because the protons and the electrons are changing their positions. So you're changing the shape of atoms when you put electricity through a wire. You're basically telling the atoms to share the pressure, and they all have to adjust to the new pressure. And the same thing would be happening in the disk because of physical stretching and pulling on the atom. So you're physically doing it instead of doing it with electricity. You're using the movement of the electrons from the inside of the disk to the outside of the disk in terms of the extra pressure. Stretching the disk a little bit, essentially, and that misshapes the atoms. And because the stretching doesn't go away, it has to constantly kind of oscillate, just like you're kind of oscillating in gravity. The key difference being is the only thing that fixes it, the only thing that stops it from continuing to fall, so to speak, what stops the atoms from flying off is the fact that there is pulling tension, holding it together, going all the way through the disk. Alright, now there's lots of other things to blame, but they don't work for each circumstance. So you could say the contacts they're using to touch the disc are bouncing because the wheels wobble a little bit and the contacts are bouncing, and that's inducing the electricity. So there's lots of other things you could blame, but that wouldn't explain this, and you could argue it's spinning in the magnetic field of the Earth, and that might be causing the effect, but again, that wouldn't explain this versus the static magnet. Let's see. Well, the magnetic field one's a little hard to say. I guess the test would be to spin with no magnet, and the disk doesn't acquire a voltage. So it just depends on how many tests you do. So if you test the disk by spinning it with no magnet, then obviously you shouldn't be getting any voltage. And if you are getting a voltage, well, then you're introducing the fact that it might have something to do with just spinning a copper disk in Earth's gravity. Alright, so the other thing noticed is all the experiments I've seen, it's all this high-speed stuff. So they really are spinning this thing fast to get this voltage. And, that's sort of another giveaway that you really are changing the structure of the disk. Alright, now, the weird part is that this ends up being a relativity argument. So that's why it's relevant to Einstein, because Einstein saw this as an argument against, essentially, his theory of relativity. Because he can't really he couldn't really argue his theory unless he has an explanation, because it appears that it matters who's actually moving. Okay, I can't just say it's a relative thing. Magnet stays still, disk spins, versus this spinning, magnet still. Okay, the two worlds should be the same, and they're not. And frankly, I don't think he explained it at all as a paradox, except to say I'm just not going to pay attention to which one's spinning. But that goes to Newton's bucket experiment, which is another experiment that demonstrates a flaw in the logic that you can never tell who's actually moving. Because Newton's bucket experiment about water spinning in a bucket sort of demonstrates that you can be certain which one's moving, because if the other one's moving, it's not going to do the same thing in terms of climbing up the bucket, fighting the gravity. So I don't know if I want to get into that complexity, but that's really why this is important in a sense, is because it's more than one paradox this gets to. That it might just be that it physically matters that you're spinning the disk and that you're changing the atoms of the copper. And that's the key thing. That's what's allowing there to be electricity, is because the atoms of the copper are being changed by the velocity. And so I think that's the real subject here, is that can this whole thing be just simply explained as, well, relativity actually isn't true. There is no equivalency principle, and that there are actual experiments you could do that will demonstrate that it matters who's moving. That it actually is a physical thing that happens, and if you looked under a microscope, a good enough microscope, you could actually see who's actually moving. So it gets to that. That's how it's connected to relativity. Because it really is an attack against an equivalency principle, where you could argue it shouldn't matter whether I move the magnet or I move the disk. And it does in fact matter, and that the induction is really being created because you're moving the conductor, not because you're moving the magnet. Alright. That's sort of the argument, to make it really simple, is that you have induction, and the point is to argue, that all you're really saying is that I can move a wire. Jeez, I want to keep trying to get something out of this, but it's just not working. So I have to give up. I sadly have to surrender. Alright, let me try this with more pressure. Well, that's not quite as bad. Okay, so I can move a wire over a magnet. Alright, and I'm guaranteed, if I move either one of these things, to induce electricity. So that's the basic experiment, is the fact that it doesn't matter whether I move the magnet or I move the wire, I'm going to create induction, because I'm going to be changing the magnetic field hitting the wire. And so the argument is that what you're really talking about, though, is atoms. And when you spin the disk, there's a bunch of little wires essentially in the disk. And the fact is you're moving those little wires. Alright. Something like that. So is that enough? Yeah, I'm just throwing this in as my context. So the real subject is, first, identify all the ways they have isolated the experiment, which is somebody's going to have to do that hard work to go through all the experiments and say, okay, here's the experiment where they spun just the disk. Here's the experiment where they just moved the contacts with the disk, the brushes. Here's the experiment to isolate what it can't be. Now, I originally thought it was just the fact that the probe wires are in the magnetic field. But you could sort of see that can't be, because, you could do the experiment where they are there and they aren't there. They're in the same place when the same thing is happening and you're getting a different outcome. So that's not likely to be the cause of the effect. It does have to be something more complicated. But you really do have to go, somebody has to do that. It's just sad that all of the experiments aren't just put in a row, so it can be understood that, okay, the disk, when it's just wobbling on brushes, can't create electricity. If I put a magnet and I just wobble brushes, it doesn't create electricity. I mean, all those things that you have to do that process of elimination thing. And unfortunately, I don't think anybody's going to do it. And that would clarify some of this about what is a possible explanation. Again, the idea of it spinning in the Earth's gravitational field seems eliminated as a cause by these two experiments. But, who knows if it's completely eliminated. Alright. So it's just my 2 cents that the important subject is, okay, first we just isolate that the real difference is the real voltage just created in circumstances where the disk has to be spinning. And there really is no way to just spin the magnetic field and cause the same effect. And if that's true, then this really is a demonstration that spinning the disk changes the atoms. Changing the atom's position is the same thing as moving the magnetic field from the atom's perspective. So you are in fact wiggling the wire when you spin a disk. Alright, I think that's good enough. Yeah, I'll call that enough. Alright, so yeah, I think that's enough. But yes, it leads to the other paradoxes the other paradox. So you could go back to Newton and say Newton's bucket experiment with water swirling in a bucket, and how you can't draw a diagram of how you create the anti-gravity effect by just spinning the water versus spinning the bucket. It goes one way or the other, but anyway, it just is another experiment that demonstrates that before you say there's an equivalency principle, that it's all the same, that it doesn't really matter who's actually moving, you have to get past these two experiments, Newton's bucket experiment and this paradox. That's probably enough. So. Okay. Yeah, that's enough. Close enough. So, just my 2 cents, frankly. It's not... I don't know if it gets to elemental physics beyond the fact that I don't think people are using the right terminology. Field lines versus lines of force versus distance from a field, a magnet, a source. I suppose this could be metaphor to like sunlight from the sun, and that what you're really saying is that for you to manifest electricity in you, you have to vary the amount of sunlight hitting you. And that's sort of the magnetic rule. And so if you're not really changing your distance from the sun, you don't have any electricity. But anything that affects your absorption of sunlight would cause the effect. It's probably not a very good analogy. So, yeah, never mind. So, till the next time and such.